Hello, and welcome to the Mathematicians podcast, the podcast where we follow the fascinating stories behind the figures that count in the history of mathematics. I'm Benjamin Cornish, and today we finally begin the Indian Golden Age with an astronomer-mathematician who reached the zenith of the Gupta Empire's academics and helped establish a new tradition in astronomy. It's Aryabhata. Today, as I record in the UK, we are going through a major heat wave, and here in my office it's recording at 35 degrees with 60% humidity. Remember kids, our bodies can handle hot temperatures, it's the humidity that will kill you. So, for the pleasure of those on the video feed, I am completely naked. Luckily, that won't interrupt the audio. But first, I recently attended a conference on hustle culture. Honestly, it's a wonder that anybody was able to be in attendance, given that they were all locked into their side hustles, each of which were presumably built different. Speaking to some of my colleagues, it appears they continued to grind on the basis that they always be grinding. This conference constituted elements of their hustle, therefore not invalidating their no days off rule. The agenda for the weekend was largely vibe-coded, with the majority of seminars starting at night, given that the attendants generally prefer to work while they sleep. One particular seminar I remember, entitled On That Grind Set, informed us that the grind never stopped. This highlighted problems I've been facing in my professional career, where I had syncopated start-stop grinding with elements of rest and sleep. I've been doing my best to eliminate that since. For instance, I now leave a permanent live stream on where people can pay to watch me eat. On That Grind Set seminar began with a long alphabetized list of beast mode peak performances, leveraging our time to help optimize everything. Naturally, the list began with alphas and betas and worked all the way down to the sigma grind set. We were locked into some deep work, but the only way is through. Towards the end of the seminar, we even embraced the grind. I would like to tell you about this particular event, but I don't need to, because success leaves clues. Ultimately, it boils down to one thing: main character energy, and I have it, winning at everything with the exception of failing the touch grass challenge. The only problem with the grind life I've been living is that eventually, having ground down everything to its unitary last figure, one finds oneself left with nothing else divisible. This is when the significantly longer task of rebuilding back to the top begins. Luckily for me, I'm in the 4 AM club, and I just decided more hustle over sleep. Today's mathematician was similarly dialed in. He chased the greatness, wake up, calculate, eclipse, repeat. Those planetary positions don't compute themselves, so leading into the infinite productivity hack, I'll show you this one trick that astronomers hate, introducing Aryabhata. And thank goodness that section is over. That took me 4 more edits than I usually take for an introduction. Born in 476 CE, Aryabhata spends his early learning in the South Indian region of Ashraka in modern-day Kerala. Possibly. His place of birth and early life are somewhat debated. We do believe that he spent the majority of his working life in the north, in the city of Kusumapara, near modern-day Patna, and at this time in history there were about 6 to 8 significant kingdoms and dynasties on the continent. He's strongly associated with the Nalanda University, which had by far the best library if you were a research scientist. It would be like travelling from a lesser-known university like Oxford or Cambridge to a more esteemed and central institution like my own alma mater, Aberystwyth. Around 1,000 miles of inhospitable and desolate countryside, although unlike my example, I'm sure the journey for Aryabhata had much better hospitality. So, the Guptas. In the last few weeks, I've done a major summary of Greek trade, Jaina philosophy, Vedic tradition. I also gave a detailed history of Babylon. Perhaps it's time to discuss the politics of India. The first recognisable empire in India would be the Nanda, a short couple of decades, 345 to 322 BCE. Notice that this is after Baudhayana and Apastamba, and this is in the north. These guys are most famous for halting the advance of Alexander the Great with their ferocious war elephants. That is the Nanda tribes, not Apastamba and Baudayana. Before these guys, there are some mentions of the Shaishunga dynasty, which was preceded by the Nagadaska dynasty. The Nagadaska Wikipedia page in English has 5 sentences, take from that what you will, and these are all formed in the Magda region, which forms the basis of the Ganges Plains. Following the Nanda, we have the much more famous Maurya Empire, which expanded out of the northeast and conquered right up past the Indus River basin and much of modern-day Afghanistan, northwest, and as far south as modern-day Bengaluru. That makes the empire like a giant rectangle that is 1,700 by 2,100 kilometres, so just over half the size of modern USA. This lasted around 140 years before decay and rot and some healthy assassinations led to a fragmentation of the empire. We then get about 200 years of messy, smaller empires, notably the Shunga, Kanva and Kushan along the north, and a much larger and more prominent Stavahana in the central region. And we are now about 300 CE. Reunifying then these disparate groups, we have what is considered the golden age of the Magadha region, the Gupta Empire. This was not an empire founded on military conquests per se, but more on political alliances, in particular those of family marriages. This dynasty lasted 230 years, and our friend Aryabhata was a young man just as it started to decline in 500 CE. The death of the Gupta Empire was mainly at the sword of the Alchan Huns. Hang on, wait a minute, the Huns are back? I thought we left the Huns invading Rome. Well, let me just do a deep dive down this particular rabbit hole. That makes more sense. So the term Hun refers to several different groups of nomadic steppe warrior tribes from around this period in history. Most notably, we see the Huns invading Rome in about 400 CE, possibly lending their name to the modern-day country of Hungary, although this is potentially disputed. And I think we call these guys the White Huns. Again, around the same time, we see people called Huns in modern-day Tibet and China interacting with the Tang dynasty. And then there's the Red Huns, or Kidarites, in northern Iran. But all these groups seem to be ethnically distinct, once considered to be a single tribal entity, invading much of the settled civilizations around the Eurasian steppes, although modern DNA evidence suggests that they are separate tribes and groups that happen to operate in the same area and with similar tactics. And of course, by the same area, I do of course mean one of the largest biomes on the planet. Now, I might stop talking about the Huns because whilst they are very cool, I'm almost certainly going to mangle the history, and it's a little distracting from our mathematical tale. After the Guptas, we see the Huns fragment into dozens of small clans, an honourable mention to the Harsha, possibly the last hero of northern unification, and you might notice that I've entirely neglected the kingdoms of the southern tip of the Indian subcontinent, and that is in part not to confuse the story of today, so I shall give an overview of that history when we meet a mathematician from the area. So, hopefully we're all caught up on the vibes of North Indian history. A rise and fall of complex and scientifically inclined kingdoms, leading to a pinnacle at Nalanda University, waiting for our hero to take centre stage, Aryabhata. When he was 23, so this is in 499 CE, he finished his first and only surviving work, the Aryabhatiya. Originally, it would have been written on birch bark or palm leaves, and in the 1500 years since it was written, the originals have all decayed. But it was a key text for his school, and as such, the work has been copied exactly. The work in museums now likely dates from between the 10th and 16th century, and you can see it on display at the Asiatic Society in Kolkata, or for a more morally questionable source, the British Library and the Bodleian Library. For me, I like to read the PDF version that is freely available online and linked in the description, translated by Walter Clark in 1930. It's not exactly a page-turner, but it's as close I'm able to get to original sources, and that's quite exciting for me. This copy has explanatory commentary, as well as examples written in modern numerals, because, of course, the original did not use a numeral system. It is a very significant work for its use of the base 10 structure, so a natural question, if it wasn't numeral, How was it base 10? So in the Sanskrit system, there were 9 words for the numbers 1 to 9, much like we have words now, and there were also suffixes to denote the power, so this could differentiate between 7, 70, and 700. Oh, hang on, that's exactly what we do when we're talking out loud. The only snag is for Aryabhata, the numbers were written down using their names, not distinct digits. For Aryabhata, the place values were written up to 10 to the power of 10, the runda, and I'm not sure how they would depict higher terms. You might notice I said there were digits 1 to 9. So did Aryabhata have a 0? Well, one of my favourite clickbait-style maths news article tropes is the idea of 0 was invented by such and such as late as such and such, or so-and-so invented calculus 400 years before the number 0, or some other nonsense. Without reading all my own back catalogue of scripts, I've possibly fallen into this trap myself when I was maybe more new to history writing. So, shall we talk about the invention of 0? Who really invented it, and when? Sadly, to answer that question, I must ask a question in return. What do you mean by 0? I would argue the invention of 0, with all of its meaning and significance that we have in the modern day, came about in many parts. Perhaps you mean 0 as an absence of something. I have an empty field with no sheep. Or maybe you wish to draw somebody's attention to an absence. The other day I had 5 sheep, then 1 wolf and 5 sheep, then 1 wolf and no sheep. Perhaps you want to use the idea of an absence itself to construct a logical statement about something that is not absent. So, beginning with 5 sheep, if the wolf eats all 5 sheep, I will have 0 sheep. Perhaps instead you wish to denote the absence using a symbol rather than a philosophical word for absence. Monday, 5 sheep. Tuesday, 5 sheep. Wednesday, 5 sheep, 1 wolf. Thursday, what symbol should I write? Or maybe this absence does not represent the whole part of something, but rather a larger part contains an absence somehow within it. Now, this last one sounds a bit less direct, so perhaps I could give you the number 1.05. That is 1 big vat of sheep meat, no medium vats, and 5 small vats. Now, this is a very contrived example, but a more fitting use would be in an astronomical table, breaking down values into degrees, minutes, and seconds. Perhaps the idea of 0 means a written numeral to join the other 9 numerals, so that rather than 100 sheep, an additional 5 sheep, you could have, say, 1, 0, 5 sheep, 100, 0, 10s, 5 1s. But in all of the above, the 0 moves from an abstract idea to a denotion of an abstract, and it's still not really classed as a number in its own right. You wouldn't be able to compute 2 plus 0, as it doesn't mean anything. With the last example, the result feels intuitive, so how about try 2 to the power of 0? Or even better yet, 0 factorial. Spoiler alert, both of those equal 1. So a quick summary of, quote, who invented 0 and when. The Babylonians in 1800 BCE used a physical gap in their tables to denote empty place value, base 60. But careful, was that 1800s or 180 or 18? I just wrote down the numbers 1, 8 and then left some spaces, so I don't really know what number was being used there. But then, 1500 years later, they took another crack at it and started using a double slanted wedge for the placeholder. So now I can say this was 15// years later. That's better. In 200 BCE, our friend Pingala used the word sunya, which is possibly the first conceptual idea of a 0 being more than just empty, but a named emptiness. A quick jump over to the ancient Americas for the first time of the podcast. The Mayan numerals used a shell symbol in 36 BCE, possibly the first full numerical placeholder. In 150 CE, Ptolemy used a small circle with a bar for 0 in a numerical fraction. This is the first 0 that non-Americans would see written down as part of a digitized number. Then back to India, we have the Bakshali manuscript, which gives the first symbol for 0, a dot, in a base 10 system under a numerical system that survived to the present day, by which I mean these Sanskrit symbols are the ones that were given to the Islamic Golden Age and then supplanted the Greek system, and so these are the ancestors to the ones on your keyboard. So this is the first symbolic 0 that is the same as our modern 0. Sorry, Mayans. This was probably between 200 CE and 900 CE, depending on which carbon dating you choose to believe. Sadly, the author is unknown, so we don't have an episode on it. I'm inclined to believe that the later dating of the Bakshali manuscript, because that would put it after today's mathematician, Aryabhata, who used the word ka. Aryabhata also gets a claim in an important step of the path to inventing 0 because he was the first to use 0 as a tool or process in an algorithm of calculation in a meaningful way. At this stage, it is still not a number. And I won't tell you who first defined it formally now. You're going to have to wait to the episode on Brahmagupta. So, who invented 0? Well, lots of people, at lots of times, in lots of different parts of the world. We all should really stop focusing on individual mathematicians and remember it's a collective effort. Agreed? Right, back to focusing on a single mathematician then. The Aryabhatiya has a few mathematical gems, and perhaps we could start with the square root algorithm. To quote, "One should always divide the non-square place by twice the square root already obtained, and having subtracted from the square place the square of the quotient is the root at the next place." That seems obvious, right? I don't think I need to give any more exposition, do I? Perhaps an example. What's the square root of 576? We start by labelling the digits square and non-square from right to left. So 5 is square, 7 is non-square, and 6 is square. Then, starting with the largest square digit, we subtract the biggest square we can think of, so 4, which is 2 squared. The digit 2 is then our first term of our solution, and the subtraction leaves us with 176. The non-square place is now 17, which we divide by twice the first root digit, which was 2. So 2 times 2 is 4. 70 divided by 4 is 4, remainder 1. So the second root digit is 4, and we are left with 16, the last square term. We subtract from this the previous root digit squared, so 16 take away 4 squared, which is equal to 0. Oh, thank heavens, it's a 0, so we can now stop. The answer is 24. Oh, you want another one? Okay. 15,129. First square is 1, first root digit is also 1. 5129 is 5 divided by 2 times 1, which is 2 remainder 1, so the next root digit is 2. So we get 1129, gives us 11 take away 2 squared is 7, so 729 gives us 72 divided by 2 times 12, which is 3 remainder 0, so the next root is 3. We're left with 09, and then 9 take away 3 squared is 0, and we can stop. So the answer was 123. Magic, isn't it? Okay, it's not really magic. It's the binomial expansion, which is technically more magic than it is arithmetic. Consider a plus b all squared. We get a squared plus 2ab plus b squared. The square can always be broken up into known terms a and unknown terms b. We then cycle through the algorithm until all the digits are known and part of the a term, and the b becomes 0. You might be thinking that if he could do it with squares, why not cubes? Good question, but Aryabhata beat you to it. The cube root algorithm is just as beautiful, although slightly hard to follow in audio-only form, but it relies on the exact same binomial expansion principle. I find it staggering that these expansions, and thus the coefficients, were something that were being played with so early on. It effectively calculates Pascal's triangle, again centuries before Pascal, although also centuries after Pingala. I also find it staggering because before researching, I had never even considered using binomial expansion for an algorithm in this way. I challenge you to recreate the cube root algorithm without looking it up. Did he do it for the fourth root? Possibly, but what possible practical use could that have? The world is in only 3 dimensions, so it has not been written down. Luckily for us, this was not his only algorithm. He also invented the Kuttaka, or grinder. This was an algorithm for solving linear indeterminate equations. So these are ones where there are multiple solutions for 2 or more variables. Consider 2x take away 3y equals 7, where the solution requires whole numbers, what we would now call a Diophantine equation. It works by repeatedly considering the greatest quotient of 2 terms. So for instance, take 137x plus 10 is equal to 60y. We start by dividing 137 by 60 to get 2 remainder 17. Then divide 60 by the remainder 17 to get 3 remainder 9. Now the 17 by 9, each time dividing the last divisor by the new remainder. So 17 over 9 is 1 remainder 8. 9 divided by 8 is 1 remainder 1, and we can stop here. Hopefully you were writing down the quotients each time. It was a list of 2, 3, 1, 1. We're now going to consider the last remainder and choose a suitable value that works with the C term. So in this case, where we had 137x plus 10 is equal to 60y, the C term is the 10. We now need to think of a number, the mati, such that if we add or subtract 10, it is divisible by the last divisor 8. So I might choose 6. 6 plus 10 is divided by 8 is 2 remainder 0. So the mati, 6, is appended to our list of quotients along with the final quotient from the mati calculation, giving us 2, 3, 1, 1, 6, 2. We then work backwards through that list, and at each stage we multiply the second to last by the one before it and add the one after it. This term becomes the new penultimate term, and the last term and the third from last term are discarded. So let's see if we can figure this out. We have 2, 3, 1, 1, 6, 2. So 1 times 6 plus 2 is 8. Slot in the 8 and throw away the 2 and the 1. We get 2, 3, 1, 6, 8. 2, 3, 1, 8, 6. So 1 times 8 plus 6 is 14. Slot in the 14, discard the 6 and 1. 2, 3, 14, 8. 3 times 14 plus 8 is 50. Slot in 50, throw away 3 and 8. 2, 50, 14. 2 times 50 plus 14 is 114. And thus the last 2 terms are 114 and 50. Although, of course, it can't be that simple, because this had a list of quotients that are even in number. Naturally, Aryabhata provides 2 versions of the algorithm, depending on parity. So with our final 2 values, we subtract from each coefficient to produce the solutions. So from 137x plus 10 equals 60y, we get x is 60, take away 50 is 10, and y is 137, take away 114 is 27. And indeed, 137 times 10 plus 10 is equal to 60 times 27. If I'm honest with you, I've run this algorithm a few times, and it's not obvious at all to me why it works. That it works is really cool, but I'm left unsatisfied on the why. I might chalk that up to my new pattern for research and writing, which is any time I get whilst my new baby is asleep in a sling around my chest, and it's slightly harder to concentrate. That and the sleep deprivation. Why we might want to do this, you ask? Well, how long have you got? No, really, that's the point. We can look at the sun, the moon, and the planets and work out how long it takes each of them to complete a cycle, moving to the exact location in the exact same direction, the exact same speed. This gives us a sense of the cosmic time. So for the moon, we have a sidereal month to return to the same position relative to the stars, which is every 27.32 days. The synodic month between full moons every 29.53 days, and the anomalistic month, that is because the moon completes an elliptical orbit, so it's faster at the perigee and slower at the apogee, which is 27.55 days. Combining these 3 gives you the Saros cycle, which is known by the unnamed ancient Babylonians, and it's a smidge over 18 years. And that is a metric smidge, by the way, not a US customary units smidge. However, even with the Saros cycle, there is a 10-degree drift and an 8-hour time difference. So we can correct this with the exeligmos. This is the Greek author unknown, but appears in the Antikythera mechanism. I don't think we've talked about the Antikythera mechanism before, but it's arguably the world's first computer. clickbait be damned. The exilegmos corrects for the drift and lets you calculate the time between the next eclipse. So it's about 3 Saros cycles, so 54 years, 33 days. If you ever see a solar eclipse, it will probably be the only one you'll ever see in your life in that spot. Don't forget that the moon moves further away on a slightly tilted orbit, giving a draconic cycle of 27.21 days. Also, the point of apogee, the furthest part of the moon's elliptical orbit itself, rotates, giving an apsidal precession of 18.6 years. And of course, the Earth wobbles, so the relative position changes given a tropical month of 27.32 days. Now, I appreciate that I've just spat a load of astronomical terms at you. You are, of course, not required to remember these. They will not be on the test later. In fact, I'm not even sure if they're on the test now, if they're still modern astronomical terms taught at university students of astronomy. But as I was taught when training to be a teacher, the students will not remember what you say, only how you made them feel. So hopefully I've made you feel like this. It's like trying to watch a kid playing with a yo-yo on a carousel that is on the deck of one boat, whilst you sit with a bad telescope on a different carousel on the deck of another boat, and then asking how long for the yo-yo to get back to the start. Luckily for Aryabhata, he didn't have access to all of these data. What he did do was, as accurately as he could, calculate the cycles for the sun and the moon, probably using the 54 years figure of the moon. And for the sun, it's debated what figure to use. Sidereal, tropical, and anomalistic cycles are all very similar. But the precession of the equinox means that the sun drifts by 1 degree every 72 years. Horoscopes get less reliable as you age. So Aryabhata may have used the great year value of 25,772 years. Also, the planets don't orbit the Earth, so calculating their periods would be even more frustrating. But, in summary, take the relative periods of the Sun, the Moon, Saturn, Jupiter, Mars, Mercury, and Venus, and now work out how far apart they are from being in alignment, and this gives you a 7-variable equation with a single constant. You can then use the grinding algorithm, the Kuttaka, to work out how many years since the solar bodies were in alignment. Surely, as God looks at the world, this is the timescale that matters, with each 4,320,000 year Great Alignment cycle being but one tick of her watch, which just so happened to most recently tock on February the 18th, 3102 BCE. And this cycle is called a Mahayuga. One day of Brahma would be a kalpa, so that is 1000 Mahayuga. Similarly, one night for Brahma is the same. During the day, Brahma creates the world and lets it play. At night, the toys go back in the box and nothing exists. That means that this world, our world, will last a total of 4.3 billion years, and we're about 1.97 billion years through. That's right, you heard me, I gave 2 decimal place value. After that, everything else will be destroyed, ready to be reformed. Now let me do a quick check. Oh, would you look at that? 2 billion years ago, we get the first proper eukaryotes, complex single-celled life that used oxygen to live. Sadly, the first eukaryote does not have a name, nor do they contribute anything significant to the world of maths, so they won't be getting a podcast episode. So, Aryabhata. He did 0, algorithms for roots, algorithms for linear equations. These are the parts that I think are cool, although I have left some more clickbait contributions to the end. In part because I think they are just not as significant. But shall we have another round of my favourite game show, Who's Got the Best Approximation of Pi? Well, at this stage, I'm sure I don't need to explain why finding pi to a high degree of accuracy is important. So, I think I'm going to go straight in with his words as translated by Clark. Add 4 to 100, multiply by 8, and add 62,000. This is the approximate circumference of a circle with a diameter of 20,000. Which gives us 62832 over 20,000 is 3.1416. Stunningly accurate, and precise enough for observations by the naked eye to line up with calculations. You should note that I give accuracy and precision as separate words, because this is precise to 4dp, and each of those decimal places are accurate. You know, I hate to compare and contrast with the Greek world, but approximations of pi are going to transcend nationality and history. They should always be viewed comparatively. Archimedes is most famous in Greece for giving an upper and lower bound of the regular 96 gons perimeter with an approximation which yields an upper bound of 22/7. So let's see what Aryabhata did. Disclaimer, he did not write down his workings, as far as most scholars believe. So all I can say is we think he started with a hexagon, like Archimedes, of radius 10,000, which would have a side length of 10,000, and then you can apply a bit of Baudhayana's theorem to find the distance from the centre to the middle of the side, using the difference of the two squares, then use this to find the distance between the midpoint of the side and the circumscribing circle. This then lets you use Baudhayana's theorem again to find the side of a 12-gon. At each step of the process, we double the number of sides of a polygon, starting with 6. For those of you who didn't listen to the Baudhayana episode yet, you can comfortably replace Baudhayana's theorem with Pythagoras' theorem, but please do go back and give it a listen. Episode 51. Here is where we hit the arms race. Both mathematicians were able to calculate the square roots, and both were relating perimeter to the approximation of a circle's circumference. But Archimedes was stuck in the Babylonian square root algorithm, whereas Aryabhata had invented his own. With this significant advantage of high precision square root calculation, Aryabhata managed an additional 2 levels of recursion, a 384 gon compared to the poxy 96 gon. What I think makes this a more delightful result is that he didn't reach pi and stop. It was not an end to itself. Instead, we see, over his career, a chain of arguments and discoveries that bleed into each other. His formulation of the square root algorithm allowed for greater precision with the perimeter of an n-gon. This in turn led to a higher precision of an estimate of pi. This in turn allowed for greater accuracy in astronomical observations. In particular, Aryabhata liked to give actual distances, rather than simply angles. For the solar system, this involved calculating the relative speeds of the planets, making the assumption that their actual speeds were identical, and then using his value of pi to calculate the relative orbits of each. Similarly, he used the shadow of the moon during a solar eclipse to calculate the relative size of the sun and the moon. These calculations are all a little woolly and rely on some big assumptions, but a more practical use of his value of pi is in turning the angular longitude and latitude into actual distances on a curved Earth, which is strikingly modern. He gives a value of the total circumference of the Earth, which is accurate to about 3%. So let's do a quick recap. Aryabhata did 0, pi, roots, grinding algorithm. Perhaps then I've left the best for last. Trig tables. Yep, you can't earn your place amongst the greatest mathematicians in history if you haven't dedicated several years to writing a big book of calculations, either arithmetic or statistical. Naturally, Aryabhata wrote a book of sine values in intervals of 3.75 degrees. For those of you playing at home, this is a right angle split into 24 segments. You might call it 225 arc minutes if you prefer whole numbers. But do you honestly think he calculated all of these by hand? Surely not. Not when he could create an algorithm. He vibe-coded his way through the function using the following formula. Sine of x plus h take away sine of x is equal to sine of x take away sine of x take away h take away sine of x, sine of h over sine of x. The keen-eyed among you will spot that this is equivalent to a finite difference process that resembles a second derivative of the sine function. And then using this to iterate through the 24 values of the sine table, where h is 3.75 degrees. We should note that the table is given in gr, which is the length of the opposite side of a circle of radius 3, 4, 3, 8. So in the interpolation formula above, the sine x does not refer to a value between 0 and 1, but rather a value between 0 and 3,438. So we can start with sine 225 is equal to 225, which is awfully similar to the law of small angles, and when evaluated with the big circle is correct to the fifth decimal. Sine 0 is 0, correct to the, every decimal place. So sine of 450 is sine of 225 plus 225, which is 2 lots of sine of 225, take away sine of 0, take away sine of 225 over sine of 225, which is 449. Instead of computing each sine, or jar, from scratch, he repeatedly corrects the previous step by an amount proportional to the current sine value. In modern language, he's approximating the fact that the sine curve bends downwards. The second derivative of sine is negative sine itself. 15 centuries before numerical analysis became a subject, Aryabhata was already approximating the calculus. Let's compare and contrast the equivalent jar of 45 degrees. So sine 45, or jar 45 over 3438, is 0.707097. Compared with the true value of root 2 over 2, it's an error of 0.0014%. So we have a table of 25 values of sine, that is 24 partitions, but it's a whole fence and fence post thing, and it's well known that you can calculate the whole circle of sine values just by using reflection. Measure your angle from somewhere else, and that means a remarkably small document can cover pretty much all of your needs. Oh, hang on, stop. I forgot there's numbers between 3.75 and 7.5 degrees. So how did Aryabhata recommend we use the table for these more precise values? Sadly, we do not get Aryabhata's own version of this method. It can be pretty strongly inferred that a basic linear interpolation was used, as this was a common practice at the time for other problems, as we discussed last time with the principle of the double false position. But personally, I don't buy it. Aryabhata is clearly using a second derivative, which would be useful if making a quadratic interpolation. Using 3 known points on either side, I find it hard to believe that he would have missed the opportunity. But hey, this is now just my speculation. Truth be told, the original values are so accurate and close together that you would struggle to generate error by using linear interpolation. That is to say, it was good enough then, and it's still good enough now. Second-order interpolation must be left to the purists like you and me and Bhaskara and the later Kerala school of astronomy and mathematics, who we will feature soon. I could stop here, and that would still be an impressive record for a mathematician working at the time. I note that his contemporaries in Rome at the time were doing far less sophisticated work. That's an opinion, of course. But there are a few more things to enjoy. The Aryabhata contains the first mention that I have come across of a generalized sum of arithmetic sequences, and then goes a lot further still. I will quote you verses 19 and 20 so you can enjoy the elegance. The sum of the first and the last term is multiplied by half the number of terms. Okay, so far so good in verse 19. This is very clearly the sum of an arithmetic series. You might call it the trapezium formula. But then check out how seamlessly that blends into verse 20. Multiply the sum of the progression by 8 times the common difference. Add the square of the difference between twice the first term and the common difference. Take the square root of this, subtract twice the first term, and divide by the common difference. Add 1 and divide by 2. This will be the number of terms. What I love about this demonstration of how you can do fairly sophisticated maths without modern notation. How poetic things become when simple bidmass rules are unspoken with talking maths out loud. The other thing I love is how we are presented with side-by-side versions of the same formula. To analyse an arithmetic progression, given first the sum in terms of a and n and d, then immediately after n is made the subject and given in terms of dA and the sum. Given that the sum is a quadratic function of n, this is essentially evidence of an ability to solve quadratic equations in the form ax squared plus bx plus c equals 0. I should point out that this is the generalised quadratic formula. There have been previous attempts to solve specific cases, e.g. without the b, but we'll see a lot more talk on this when we get onto the cloak and dagger world of solving partial cubics. Not to be outdone, Aryabhata casually drops the formula for the sum of squares, the sum of cubes. As every further math students will know, he didn't need to because they're always on the formula sheet. Not sure why he didn't check before deriving them. And he also mixes in solutions for calculating interest on loans, which is a lovely thing to mix in, as the solution is evidently analogous, but the context is different. It's the same way that textbooks are written today. The last point of the Aryabhatiya, which I should mention, is the elusive continued fractions. Many of my sources, though MacTutor, the Aperiodical, and Wikipedia, make oblique reference to the Aryabhatiya using continued fractions. This filled me with delight, as continued fractions are a fascinating entry point to arcane number theory. A quick explainer: a continued fraction is one where the denominator itself is given as a mixed fraction, a whole part plus another fraction that is in turn has a denominator that's a mixed fraction, and the ladder descends ever down. Using this, you can represent some pretty cool numbers. For instance, the square root of 2, which is 1 over 2 plus 1 over 2 plus 1 over 2 plus 1 over 2, etc. As it turns out, reading through the Clarke translation of the Aryabhatiya, I can't find any evidence of continued fractions studied for their own sake in this infinite regression form. What we do have, though, is a use of a continued fraction in solving the Kuttaka method, the algorithm we discussed earlier for division. Although it's not explicitly stated, the method is essentially using a recursive divisor representation. The example Clarke gives, which we discussed earlier, was 137 divided by 60. As a continued fraction, this would be listed as 2, 3, 1, 1, 8, or 2 plus 1 over 3 plus 1 over 1 plus 1 over 1 plus 1 over 8. I am going to choose to not give Aryabhata the credit for inventing this number form, but he certainly has the potential to inspire someone to come along and generalise the idea. So this brings us roughly to the halfway point of Aryabhata's contributions. We've picked out all the juiciest fruits from the Aryabhatiya, but he also produced another great work of science, the Arya Siddhanta. Let me just check my notes. Oh, hang on, I've lost them. Which is just as well, because so too has history lost the Arya Siddhanta. We do have reference to it in other later works, so we know that it was a book on computation. It included descriptions of tools and methods, including references of two different designs of a water clock, bow-shaped and cylindrical. Oh, what fun we could have had reading that together. Although there is some evidence that it was not an original work of Aryabhata, but based on the earlier Surya Siddhanta. This is because Aryabhata is inconsistent with his metric for the start of a new day, midnight versus sunrise. So, that's that then. There is a third work as well, whose original Sanskrit name is lost and the content is lost, but we think the Arabic title was Al-Nanf, and it's referenced by Al-Biruni, who claimed it was a translation of Aryabhata, but I have even less to say about this, so we should probably just leave it there. And this is probably a good time to start wrapping things up. We have Aryabhata, one of the great leading lights of the late ancient Indian mathematics. He gave us a few new tools with finding the second and third roots, used these tools to create recursive algorithms for approximating pi better than anyone before. He riffed on recursive algorithms further and solved indeterminate equations, a quick loop around quadratic equations and the sine table with hints of second-order differentiation, and he gave the nascent concept of zero just a smidge more meaning. This one definitely falls into the category of great man history, and I'm not ashamed to admit it. That said, next week we are moving into a mathematician who was very much not a great man of history. So far, in fact, that I was debating whether or not to include him at all, Varahamihira. A less inventive mathematician in his own right, but a preserver and caretaker of wisdom and the great schools of old. Looking ahead as well, I can see we are approaching the end of our Indian-Persian series, which will finish with Brahmagupta. and it would be nice to fit that into episode 60. We like round numbers. So next time, Varahamihira, with perhaps a small side order of another minor mathematician, followed by Brahmagupta, after which I will need to decide where to follow the strand of history next. The main choices are finally start the Islamic Golden Age in 800 CE, go to medieval Europe and work 800 up to Fibonacci, or head over to China and start again from the earliest records. If you have a preference, post a comment below and I will certainly read it. Or you can always reach out to me on Blue Sky at mathematicians-pod, and I also plug my Ko-Fi page from time to time if you want to support the show, but also to let you know that I do take commissions. So if you would like me to prepare an episode, research, write, produce, and send it directly to you about any mathematician you like, you can let me know. Then, when the time comes for them to slot into the chronology of the show, I will publish it to the main channel. But until then, it can be just for you at home. Who knows, maybe you have a great-grandparent who is a mathematician and would like to make a homage to them. Details in the description. Otherwise, I will see you back here for Varahamihira next time on the Mathematicians podcast. Until then, goodbye! But before I go today, I have some exciting news to share. I have my very first sponsor. That's right, I've become a corporate shill. Well, not so much. It's actually just somebody I met on the internet and immediately entrusted with my personal contact details. So he has developed a new game that I think is a fabulously fun idea. It involves walking around the world and claiming territory as your own. Something about it speaks to the historic Englishman in me. You may claim a 50 by 50 metre square of the planet, give it a name, write a little message, yours forevermore, with the only rule that you have to be standing on the square to claim it. I'm already in the process of trying to capture my village in the name of the Mathematicians podcast. I think it's quite fun and a good reason to get out of the house for a bit of a walk. And you can start capturing your own tiles on www.tile.today. It's free, so I can't really offer you a discount code, but if you want to colour a square and add a link to the podcast page, well, I won't stop you. The music today is Dance Macabre Finale by Kevin MacLeod. You can find more information in the show notes.